Okay. Yeah, they just did a big upgrade. Zoom did. I think it hit this morning. So things are a little bit different than they were last week. Okay. Can everybody hear me okay?
Mm-hmm.
All right. Today we're going to wrap up some stuff on quadrature that I promised I'd go over, and then we're going to move into finite elements. So let's begin. Share my screen. And if you've glanced at the wiki, we've got the first two homework keys posted, so you can leverage that to now see if there was any holes in your understanding. And for those students who are taking this for a grade, I've also posted some self-grading exams where you basically take the exam and give yourself a grade. You guys seen that? Have any of the students looked at that?
Yeah, I went through and did 2 of those this morning. It was really straightforward.
Okay, great, great. And then the key, I hope, also makes it possible for those who aren't taking it for a grade. You can kind of at least think about the questions and see how they're worked without maybe having to put in quite as much effort. Okay, what I wanted to do was talk about quadrature. If you've ever used finite elements, maybe at first glance this appears kind of like an esoteric topic, but it is really a big deal in finite element methods. And in fact, if you're just a user of the software, it's a big deal because you make all kinds of decisions with regards to how quadrature will be used for a given finite element run. So let's just start. I want to just spend a few minutes on this. I want to give you some really good mental models for exactly what quadrature is doing, because it kind of permeates the use. Once you understand these mental models, you'll begin to see, like, okay, now I understand why quadrature is something I care about in this instance. So let's talk about, let's begin just talking about interpolating polynomials. And these bases, these classical polynomial bases, a lot of them were developed in the context of this problem. And what this problem means is either you've got a discrete point data, let's say, where each point basically has an xi, yi point. So this is one version of this problem, or you may actually have a function f of x where you want to try and construct an approximation to f of x given some points. So in this case, it's xi f of xi. And so interpolation really is about, if I give you these discrete values, can you fill in the gaps with polynomial approximations? So the basic idea is, if I give you these points, how do I construct a polynomial? And it's really just a linear algebra problem. Okay, so you go ahead and you pick a polynomial basis. Of degree, let's say I give you n, just to keep it consistent. Let's say I give you n minus 1 points. So that's how much information I give you. So then you have to pick a polynomial degree basis of degree n. Is that right, or do I have that wrong? Let's see. It's the other way around, I think. Yeah. Okay. Okay. Pick some points. Okay, and then the last step is you want to create a bunch of equations. So let's pick some point. Let's say we pick this point here. We want to construct a polynomial that passes through that point. So why don't we say, or let's use, just for simplicity, let's use the power basis because it's easy, which is 1x, x squared, and so on, up to x to the n. So we want 1 plus x evaluated at our first point, x1 plus x1 squared plus, let's give you some constants. Let me just read this. Okay, we want to find a polynomial in the space spanned by the monomials. So we want to come up with some a plus b x naught plus c x naught squared plus, I don't know, whatever, f x n. Actually, this is x, n equals f at x naught. Okay, so do you see what's happening here? What I've said is I'm going to pick some polynomial, an arbitrary polynomial out of this space with arbitrary coefficients. And at x naught, let's say x naught's right here. This is our x, say this is our x0, f at x0 point right here. We want the polynomial that we pick to be equal to f of x naught. So this gives us equation number 1. Okay. And then how many times are we gonna, how many equations are there going to be? Well, if there's n plus 1 unknowns, a, b, c, d, e, right? There's n plus, these coefficients are the unknowns. So we need to have n plus 1 equations, but that's good because we have n plus 1 points. So each point corresponds to an equation. Let me clear this and so we end up with a matrix that looks like 1s, and then x naught, x1, x naught squared, x naught, I guess it was 1. Then we have coefficients a, b, c, and then that's equal to, oh yeah, I'm getting confused on the indexing here, guys. Keep me straight here.
So wouldn't you only need the number of equations for how many coefficients you have? You wouldn't need the number of equations for how many data points you have. Unless,
you need enough, yeah, if you have n plus 1 unknowns, you need n plus 1 equations.
right, but you have more coefficients than you have data points potentially. And you're gonna have to solve for each one of those coefficients. So you'll need, in order to solve for those coefficients, don't you need as many equations as you have coefficients?
I'm sorry. Will you say that again?
Well, so data points, right? That's your f of x, right? And you could have more data
you could
points.
do like a least squares fit, right? You could fit like a linear function to like 20 points.
Yeah.
Right? And you have to solve that in the least squares sense.
Right. And if you only wanted to do linear, you only need as many equations as you have power. So if you did an x, you only went up to x, you didn't do squared, and you just wanted to do it with a linear equation, you would need two equations to solve for the two unknowns, which is a and b. You wouldn't need to solve for as many. You'd only need a couple of those points and do least squares fit.
But that's just not the problem that we're looking at. Yeah, that's a different.
Yeah, so I think the assumption was there's n+1 points that we're trying to fit, right?
Yeah.
But I guess my underlying question is there a reason why you're going, like, is there a way to know how many of those up to n coefficients, or I mean powers, you need?
If you have, if you have n+1 points, you need an nth degree polynomial basis.
Oh, okay.
Yeah, you can even see it in this equation here. Let me change this notation slightly so that it's a little bit. Let's call these coefficients just C0, C1, right? So you have C0 through Cn, which is n+1 unknowns, but you're sampling at n+1 locations, which gives you your n+1 equations. And so you have this is a square. This is let's see, n+1 by n+1 matrix. Anybody know by chance what this is called in the power basis? It has a name. Starts with a V.
Vandermonde?
Yep, Vandermonde matrix. And so if this matrix is invertible, you can solve for the coefficients, and then you can reconstruct your approximation. Let's call it maybe f of x h. Your approximation is then C0 plus C1x plus C2x squared. That will give you a polynomial that's going to go through these points, right? It may not be exact, but it's going to give you something that's exact at the points. So the point here is that I can take a function f of x, and I can approximate it with an interpolating polynomial. And let me use some notation that's common in finite elements. Let's use big U, H, to denote the interpolating polynomial of f. Okay? And what's important for you to see is that as the number of points go up, the degree of the polynomial goes up. And the point locations, notice that this matrix, you see how strongly it depends on the point locations? So as you move the points, the interpolating polynomial changes. Okay? So you have some nth degree interpolating polynomial, but the coefficients are going to depend on the locations that you choose, right? Everybody okay with that? So where these points are, right? Like, so x0, x1, x, I mean, you can move these anywhere you want. What's the only thing you can't do with these points in order to make sure your matrix is well formed?
Mix them up, put them in a different order.
Well, they could flip position, then you just relabel, but they can't go on top of each other. You can't have a coincident point, because then you'd have two equations that were the same equation, and that would be a linear dependency. And in fact, this matrix would be then singular. Okay. Okay. Now you might be asking, what on earth does this have to do with integration, which is the point that I'm trying to make here? And it has everything to do with integration. Because integration, when you choose a quadrature rule, you're choosing an interpolating polynomial. So think about that for a minute. What do you get? Let's erase and start over here. Quadrature is, let's say we've got some domain. Let's use the classical domain -1 to 1. And you specify, let's say, n points and n weights. Okay. So how many degrees of freedom? So if this is a Gauss quadrature, your degrees of freedom really are, you're free to choose the point locations and the weights associated with those points. So let's now switch to quadrature and show you what the implications are of those choices. Okay, so we have some integral. Just to be consistent with my notes, let me make this the same here. Okay, we have some integral, a, b, and an integrand. This is what pops up in finite elements, and then we say, I'm going to pick a quadrature rule. And normally what we mean in finite elements is that we pick a Gaussian quadrature rule. And a Gaussian quadrature rule actually means that you're free to choose not only the n points, but the n weights as well. Okay, so in this problem, you're free to choose 2n, you have 2n degrees of freedom, which means that you're going to need an interpolating polynomial of degree 2n minus 1. So let's write our interpolating polynomial. Be approximately equal to big UH.
Mike, why do you need it to be 2n minus 1?
Well, because if, you know, like how many coefficients, so these are the unknowns, right? And remember the unknowns correspond to the coefficients of the, so you have C0, C1x plus C2x squared plus, and then we go up to like C. So how many degrees of freedom are? There's 2n, so that would be 2n minus 1, right? Because we start with 0.
Oh, yeah, that's right.
And then this is x to the 2n minus 1. So guys, when you pick a Gauss quadrature rule in finite elements, what you're really doing is you're saying, I want to interpolate the integrand the best that I can with a polynomial of degree 2n minus 1. And the point locations and the weights that I pick are going to tell me what the nature of that interpolating polynomial is. So let me keep going with this derivation.
Dr. Scott, I have a quick question.
Yep.
So in general, when we interpolate a polynomial, I'm assuming you don't usually use the power basis, like we use either the Bernstein polynomials or like Legendre?
Great question. Yeah, that's you're leading me right into the very next line of what I was going to write here. So in Gauss quadrature rule, they do something very specific. Okay, so this is our interpolating polynomial. The next step is they say, okay, well, I'm free. See, this is unique. You can show that this interpolating polynomial for the right number of points is a unique polynomial. So it's independent of the basis that we choose. It'll be the same polynomial. So why don't we choose the Lagrange interpolating polynomial in terms of the Lagrange basis? Because that one we know interpolates in a very simple way, right? You just simply set the nodal values or the coefficient values equal to the function evaluated at the point location. So we're going to pick we're going to pick in particular the Lagrange interpolating polynomial in terms of our Lagrange basis, right? Which, and our Lagrange basis is usually defined between -1 to 1, which also explains why Gauss quadrature is always from -1 to 1, is because of this decision in the Lagrange interpolating polynomial. So just to remind you what those guys look like, if you come up here, here's the Lagrange polynomials. Okay, and it has this interpolation property, which is why it's chosen as our initial representation of our interpolating polynomial. So let's see. All right. Now we write our UH in terms of a Lagrange interpolating polynomial, which is nothing more than I equals 0 to n of f of xci, the Lagrange basis function Li of xc, d of xc. Okay, and then we can invoke linearity and show our next step. We can pull the sum out, and then you should start seeing that, oh wow, this looks like a quadrature rule. And this is f okay, and then the last step here. Running out of room. Let's come up here, guys. Can you? And our last step is just noting that okay, so that's our quadrature rule. Now, what I think is really kind of cool about this is that over here is the same thing I just did. Is this suddenly tells you a lot about what your choices are. If I choose an endpoint Gauss quadrature rule, I know that I'm picking an interpolating polynomial of degree 2n minus 1 because I have n weights and n points. But irrespective of that, given an endpoint rule, it generates a particular interpolating polynomial, which then can be interpolated using a Lagrange interpolating polynomial, and that tells you exactly what the weights are. What are the weights, guys? You might have wondered where the weights come from. What is this?
It's just the integrals of the basis functions, right?
Yeah.
This
It's
is cool.
it's just the area underneath each Lagrange basis function, and you should check that. If you compute the area underneath a Lagrange basis for different polynomial orders, you'll see that they are the Gauss-Legendre weights. And so then the weights are nothing more than the area underneath. So in other words, what you're doing in quadrature is you're taking a weighted sum of function points times the integrals of the Lagrange basis functions, which is kind of a cool way to think about quadrature. And so now the last decision you have to make is, well, what are the point locations? Remember, I told you that the point locations, every point, the interpolating polynomial is unique with respect to a degree and a set of points. So every point, every set of points will give you a different interpolating polynomial. So the question then becomes, what's the best point locations? And it turns out that you can show that the point locations that you want to pick are ones that are the zeros of a class, some class of Chebyshev polynomials. And the important thing is that Chebyshev, it minimizes the Runge phenomena. So it minimizes oscillations. If you pick your CIs to be the zeros of some Chebyshev polynomial, it minimizes the Runge phenomena. And conceptually, what it's doing is it's putting more, it puts these kinds of, the zeros of these kinds of polynomials, they put more points at the ends. You think about Gauss quadrature, it puts more points at the ends, right? And that's because the Legendre polynomials, for Gauss Legendre quadrature, we take the zeros of the Legendre polynomials, which are a class of type of Chebyshev polynomial. And those zeros give you an interpolating polynomial of a certain degree that minimizes the Runge phenomena because the points are placed in a particular location. And so that's how that's why we pick the points that we do, is because it all goes back to this interpolating polynomial question. If I have an integrand and I want to know how to integrate it numerically, I say, okay, I'm going to find an interpolating polynomial of some degree. That's going to depend, the higher the degree, the better the higher the degree, the more quadrature points there will be. But if I can find a good placement of those points, I know that I will get a good approximation to the integral. So that's what finite element quadrature is all about. I mean, that's how it works. So when you pick, so for those of you who've used finite elements and we use reduced quadrature, somebody now reason for me, see if you can say it out loud, like what's going on there with reduced quadrature?
There's less points to solve for.
Okay, so there's less points, but why would we be taking less points? Because that will give an interpolating polynomial of lower degree with less accuracy.
Does it improve our conditioning by it no longer has to exactly interpolate?
Okay, so we normally do this for a phenomena called locking. So we say, I don't want to lock, so I'm going to pick fewer quadrature points. What it means, guys, is you may have picked a finite element basis, let's say, of degree p, right? Maybe this integrand is written in terms of some degree p finite element basis. But when you pick a low quadrature rule, you're throwing this out. And you're saying, well, through quadrature, what I'm really doing is I am using a basis of maybe degree p minus 2. You see how quadrature, it can raise, or it can lower the degree. It can lower the fidelity through the points that you pick because that defines an interpolating polynomial. So if you have a space that's not quite right for your physical problem, you can actually cast the problem, project the problem into a totally different polynomial space than your finite element basis through the selection of a quadrature rule. That's the punchline.
So Mike, this brings up a question that has always seemed counterintuitive to me. So how is it then that when you raise the degree of your interpolation basis, your integrand in this case, you reduce locking?
Because, well, those are two separate effects. Yeah, so you can also raise the degree, which means that you can get rid of locking through refinement too. So,
sure. So when you say that your reduced quadrature is like having a p minus 2 interpolation, that's not quite right. It's more like you're mapping to a slightly different space that's reduced.
Yeah, that's what I'm trying to emphasize here, is that through quadrature, locking says I don't have my spaces, my finite element spaces quite right, so I'm locking up. So rather than trying to figure out exactly what those spaces are, let me use quadrature to map into spaces that should be better suited for the problem. So sometimes you'll take the strain and you'll split it, right? Like into a shear part. Maybe you'll split the strain into shear and bending and membrane. And then you'll do like integration over the part that you don't, that's giving you locking. And you'll do like reduced order on shear. So that what that's equivalent to is a mixed method where you're integrating certain parts of the strain with a degree p basis, but these locking parts you're integrating with like a p-1 basis. But rather than actually constructing the mixed problem, you do it implicitly through quadrature. That's what reduced quadrature does. It mimics the behavior of mixed problems without having to build the mixed spaces.
And just to be clear, it's not exactly the same as a reduced order space. It's just similar.
No, in many cases, you can show it's exactly that. That's exactly what you're doing. Is the way that you solve mixed problems in locking is you usually pick like a primal space of degree p, and then some subordinate bases of degree p-1. That's usually the way that it works. So anyway, that's all I wanted to say about this. And so what's the mental model that for me, having used finite elements for years, that's valuable here is it helps you understand. So let's just go through a little exercise. So here's question number 1. What are quadrature points? Let's see, who wants to answer that? So now, what are quadrature points?
Are they places to sample your function?
Okay, that's true. This one's places to sample the integrand. Okay, what else?
Are they the control points for your interpolating polynomials?
Exactly. They're going to determine the f of xci, right? Which are the coefficients of your interpolating polynomial.
Yeah, thanks. That's a little more precise than what I said.
No, that's right. The coefficients of the interpolating polynomial. Okay, what else are they?
They're fun.
Okay, they're fun. So what's the strategy behind how we pick their location? Like, what are we thinking about when we pick the location of the points? What are we trying to minimize or maximize?
Runge's phenomenon.
Okay, you want to minimize oscillations. Okay, and so because we want to do that, we're using Chebyshev-like bases. Yep, so basically you're picking them to get the best interpolating polynomial that you can. Okay, so that's really what quadrature, so that's how you should think about quadrature in finite elements. It's very important. It's related to a space. When you pick quadrature, you're actually picking a space, and quadrature actually determines the space, the final space that you end up using in your approximation. You know, because everything else can, if you get your quadrature wrong, it doesn't matter what you thought your finite element basis was, it'll change the problem. So question 2 is then, what are the weights? this one really is pretty easy. We already went through this, so maybe I'll just answer this one. It's just the area under, and this is really, we're really talking about Gaussian quadrature here. Under the Lagrange polynomials, Lagrange basis. So I don't know, I mean, I'm a little strange, so these kinds of things are really exciting to me. Like just going through that, I feel pretty jazzed about just having talked through that. And I realize that maybe some of you are thinking that's the dumbest thing I ever heard, or it's really boring. So I apologize ahead of time. Anybody else though think that that's pretty cool to think about it that way?
I really like the perspective. I also would like to kind of see it in terms of maybe an application. So this is still pretty high level, but is there a way that we can bring it to something maybe we've seen in the past and say, this is how it relates? So like, for example, if you're picking, if you have a shell, right, and you're going to pick the quadrature points on it, and you're trying to query that shell for responses, how do those values that you're solving for relate to the response that you're seeing?
Okay, so practical application, I would say, the first thing I would say is any problem that locks. So these are, let's say, beams, shells. What's that?
I was muttering pretty much everything. I thought I was on mute.
You know, incompressible elasticity. Stokes flow.
Do plasticity.
Plasticity. Let's see. Contact. Electromagnetics. So any problem that locks, you can treat through this idea of quadrature creating the appropriate interpolating polynomial.
So what is locking mathematically? I've heard about this phenomenon before, but my background really isn't in finite elements. So
okay. Locking. Yeah, I need to add it to the notes. I noticed that we talk about it a lot. We haven't really discussed what it is. So let's say you had a beam bending problem and you knew the exact solution was 1. Let's say U exact was 1, but when you discretize it into elements and you solve the problem, maybe you get a displacement of 0.000001, something like that. What we say is that it's locking because you can see it's locked up, right? It's not moving. And one way to think about this is that you have so many constraints. One way to think about locking at a high level is that there are so many constraints the only solution is to not move at all. You know what I mean? Like, even in life, right? Sometimes don't you feel that way? So many constraints, I just freeze up and I don't do anything. Locking, that really is the phenomena. What it's saying is that you have imposed so many constraints on your problem that you can't find the solution. You're over constrained. And this phenomena happens a lot. Like, for example, if you have a problem where the strain was supposed to be, the strain equations were supposed to be satisfied, let's say, in some degree p-1 space, but instead you satisfy those constraints, those strain constraints. Maybe you pick like a p+1 basis. Well, the number of constraints is going to be the number of nodes, right? It's going to be the number of finite element equations that you have. So if the space is too high of a degree, you're over constrained, and the problem locks up because it's harder to find a flexible, appropriate solution if you're over constrained. And so there are constraints built into a lot of physical problems that may not be totally obvious. Incompressible elasticity is a little easier, right? You have an actual constraint, a second equation that's imposing that the divergence of the stress is 0, right? That's a constraint. And if you apply that constraint in too many locations, your solution will lock up. And in fact, there is in fact, that constraint actually has an optimal number of constraints with respect to the primal basis that you're using for displacement. And that relationship is what's encoded in what's called the imp soup condition, or the LBB condition in mixed methods. And so that's why in finite elements we use reduced quadrature, because really it's a way of doing a mixed method with some other space in an easy way. I don't know if that was a good description or not.
I guess I'm trying to get a grasp on it. So when you say over constrained, do you mean like, when you get down to like the matrix that you're trying to solve?
Oh yeah, okay, here we go. Okay, if you're looking for a matrix, okay, yeah, sure. Here's a matrix these are the matrices that come out of these kinds of problems. This is kind of the canonical matrix, all right? This guy right here is usually symmetric positive definite, so this guy's in good shape. These guys right here, we sometimes call B the constraint matrix. And so the question becomes, right, like these columns correspond to like the number of nodes, and these rows correspond to the number of constraints. What you want to show is that as the number of nodes goes to infinity or gets really big, that in some sense the constraints grow at the same rate. Otherwise, you're going to get a matrix that's infinitely tall. And what that's going to mean is that in the limit, you're going to engender linear dependencies in your constraints. That's another way of viewing locking.
Okay.
Can you demonstrate that on this beam? Like, could you see this if you just used the direct stiffness method?
No, you can't in the beam because the constraints are embedded in the strain. And so I'd have to look up, it's not obvious how to deduce those. The easiest problem is really incompressible elasticity or Stokes flow, or even adding any kind of a constraint like a Lagrange multiplier. In fact, we're going to do that next. So, if this matrix gets really tall and skinny with respect to how this is going in this direction, then you get singularities. And so what quadrature does is it reduces the number of rows. It controls the number of rows that you add because the rows are associated with the quadrature points. That's another perspective. I don't know, maybe that was more what you were looking for, Ryan.
I think so, yeah. It would be good to see an example where this, kind of, you can kind of derive this scenario.
Yes, I think we'll have an opportunity to do that because with spline methods, we construct a lot of these. So I'll be on the lookout to see if I can come up with a good example.
Okay, Thanks.
Okay, that's all I have to say about quadrature. Boy, it took the whole lecture. My goodness, I must be, either I have a lot of informative things to say or I just blabber and most of what I say is not valuable. I don't know which. I can't see your faces. I don't know. It's like I'm talking into the abyss.
Now, Mike, when you do reduced quadrature on a beam, that's not necessarily going to make you get the right solution.
You have to use it correctly, right? There's a theory that guides the selection.
But in general, you can't use those reduced quadrature elements and suddenly use solid elements on a beam.
Well, you have to be careful. Yeah, you have to know what you're doing. Yeah, there's no free lunch. The point here is that quadrature, if you don't have this picture, it's completely meaningless, right? Like if you don't understand what's going on underneath, it seems completely arbitrary what we're doing here. So, okay, great. So we're done with the preliminaries now. Next lecture, we're going to get into finite elements, and I'm going to be teaching finite elements in a brand new way from the standpoint of splines, meaning that we're going to develop from the very beginning the methods that are optimally suited for taking advantage of what you get from splines. And it actually penetrates way down to the very foundations of how we build methods. And so I've decided to just teach that ab initio as if it was the way that you learn finite elements. I'll try and point out, you'll learn finite elements, classical finite elements are subsumed by this approach. So you're not going to lose any information, but it just really does change the way you think about these problems. So I'll try and lay that out. So let's go ahead and end here, and I'll stick around for any questions for a few minutes, if there is any.
I have some if no one else does. Can I go ahead?
Yeah, go for it.
Okay, so suppose you're doing a classic blocking problem like that membrane locking problem. If you're doing exact quadrature, so you're exactly integrating your shape functions, and you raise the order of your shape function, your locking will go down, correct?
Yep. Well, it will go down whether you increase the number of elements or increase the degree.
Right. So then, but then if you do reduced quadrature on the same problem, locking goes down. So it is like mapping to a different interpolation space.
Yeah, that's right. That's exactly right. You can always overcome these problems by just refining the heck out of the problem. But the point is you're just kind of kicking the can down the road in that case. You're not actually solving the problem. You're just...
Well, the reason I'm asking this, Mike, and restating it the way I am, is because in the lecture a second ago, you said that in certain cases you can show that it is exactly the same as having a reduced order, like reducing P.
Yeah, so
that's
you
what I'm
can
trying to get my head
go,
around.
if you have like a structural problem, let's say like beams, something with beams, shells, solids.
We'll just say it's incompressible, so it's really simple to understand.
What I'm saying is usually you have some nodal FEA solution. Let's say you pick degree P. Just you use the same degree everywhere for everything. There's displacement U of degree P, something like that. Okay, for everything. And that guy may lock. What I'm saying is the right way to do this is to come up with some mixed method, let's say mixed exact method, where you then have maybe like stress is an unknown, maybe you have strain as an unknown, maybe you have displacement as unknown, and they may have all different degrees, right? Okay. Usually usually the problem though is sometimes we don't even know what this problem is. We know it locks, like for shells, like membrane locking is a good example.
Mhm.
We know there is some exact mixed method that would, we know that it exists, but we don't know what it is. We don't know how to write it down. So what we do instead is we circumvent this and we just go, what we do is, let me erase. What we do is we just go like, we go back to this problem with reduced quadrature. The fact of the matter is, Curtis, is we don't know. Only in the simplest cases can you write down the mixed problem that's exactly equivalent to reduced quadrature, especially in these structural theories. If you're doing like Stokes flow or something really trivial, then sure, the constraints are really obvious and you can figure out exactly what the right interpolation spaces are and all of that. But for structural problems with this kind of locking, we don't always know what the mixed method is. And so how do we circumvent that lack of knowledge? We just throw reduced quadrature at it. So if you're looking for me to write down like the exact mixed problem for like membrane locking, I don't know if there's anybody in the world that could answer that question.
So when you go to these substantially different spaces, like going from a linear Lagrange world to splines, your intuition for what causes locking may be a little off.
No, it's the same. It really
I mean,
doesn't.
you're not going to get different kinds of locking with a
Nope.
with a space that's different
Nope.
like that.
No. Yeah. Splines will help. I mean, splines they're more powerful at kind of kicking the can down the road on locking.
Mm.
But so from a practical point of view, we often just like rate. Well, we'll talk about it. We do. I'll tell you exactly what we do with reduced quadrature for splines. But it's the same theoretical idea. Everything's the same.
Thank you.
Well, no problem. Anything else anybody wants to talk about?
I have a quick question real fast, Dr. Scott.
Sure.
Could you go so like on this side there's 30 and 31. Could you go in between the steps of how you got from 30 to 31? I don't quite see it right now.
Sure. So this guy right here,
Right.
basically we're saying UH is equal to the sum F of XCI Li. This is the this is just this right here. The way I would say this in words is that this is the this is the interpolating polynomial in the Lagrange polynomial basis.
Of F or of UH?
Of F.
Okay.
Yeah.
So the two F's there are different then?
Nope, this F here, what I'm saying on the first line is that there exists some, this is the interpolating polynomial for a given set of points is unique. So that's what big UH is, independent of basis.
Okay.
Then I say, well, let's go ahead and represent it in the Lagrange basis. And that's what this statement is.
Okay. Sweet, thank you.
It's nothing more than saying that I'm going to choose to represent my interpolating polynomial in the Lagrange basis.
And the n in that summation is a typo. N equals 0.
Yeah.
It's supposed to be I equals 0. Okay.
Yep.
Awesome, thank you, Dr. Scott.
Mhm. Yeah. I don't know. Does anybody else think that? I just think that's like, I don't know, that's a powerful mental model if you're working in numerical methods. Is there anybody else out there in the abyss that feels the same way?
Yeah.
mean, I've already said that I think it's really fun.
So I've only ever seen this stuff from the math perspective. So all this, what you went over is review. What I'm trying to get a better idea for is the engineering side of things. So
Same for me too.
I think I'm trying to connect the two at this point.
Yeah, that's where I'm at.
Hey, I have a question about this. So we're picking the points to minimize Runge's phenomenon.
Yeah.
And that's locally within an element. So that helps us somewhat, I guess, but it doesn't really solve the problem like when we look globally where we have many elements connected together.
Yeah, let me show you what it looks like if, what you can, yeah, so Runge phenomena can show up also, right, so when you connect multiple elements together, that creates a C0 spline, and C0 splines can also suffer from some of that Runge phenomena, not quite as much. Smooth splines are much, much less. But yeah, when you connect them together, you're connecting a whole bunch of little C0 pieces together. You can also get it in that context as well.
Okay.
In fact, splines were originally really one of the main motivations behind their invention was to overcome Runge's phenomenon. Yeah,
Okay.
so you'll see this. If you take a polynomial, if you take a like a bunch of finite elements and connected together, and then you try to approximate something that looks like that, no matter how many elements you get, you're going to get these, these overshoots and undershoots. C0 is worse than smooth, but you'll still get them.
Yeah. Another observation here is, so the fact that the weights are the areas under the Legendre functions. So if you have like a second order finite element based on Legendre polynomials.
Lagrange, it's the Lagrange.
Sorry.
Lagrange, yeah.
So the weight is a lot higher for that middle one than it is for the two end functions. So for the one that's one at the middle node.
Yeah, here they are.
Yeah, like on the left there, the yellow line.
Yep.
The weight for that one's like, I looked it up, like 0.866 or something, where it's like 0.5 something for the other two.
Yep.
So that, I guess, means that the response is dominated by the behavior of the middle node in some way.
Yep. Yep, and that's intimately tied to the fact that why we like to have more points towards the outside. It kind of, and I don't even, I mean, there's subtleties here that I don't even, I can tell that there are some things here that even I'm not grasping, some relationships that I'm not seeing myself. There's a lot here.
Mike, when you don't space those correctly and you get Runge's phenomenon, how does that manifest in your solution?
Oh, you'll just get really high integration error. So if you looked at a convergence plot or something where you weren't integrating correctly, normally what you have is your approximation error. Let's say this is your approximation error. Okay. And normally with Gauss quadrature, it's going like Gauss quadrature usually converges really fast. Right? So what that means is like asymptotically as h goes to 0, this guy, your quadrature error will be dominated by your that's what you want. You want your approximation error of your method to dominate. That should be the rate that you see asymptotically, and quadrature should always be out of the picture. It should converge faster. If you pick the wrong points, what happens is that now maybe your quadrature error converges like that. And so what will happen is you refine your mesh is it'll converge it'll converge at a correct rate. And then at some error level, it'll get washed out by your quadrature error. And then the quadrature error will actually dictate the overall accuracy of the method.
Are you going to derive the theoretical convergence rates for us? Like show us why that is what it is?
I already did. It's actually in the interpolating polynomial. It's here they are. I didn't go over them, but so in finite elements, you compute. I mean, the basic idea is you compute this little UH, and you know that's the best approximation according to Gaussian. So you know that its error, the error of little UH, has to be less than the error of the best interpolating polynomial. And then you use these guys to bound this error. And that's where you see here you get your h to the n plus 1. That's it. That's all. That's basic error analysis for finite elements. Is you just all you do is you play tricks with norms until you can bound your Galerkin solution by your interpolating polynomial, right? Because it's the best guy, so it's better than the interpolating polynomial. But the interpolating polynomial is bounded by these estimates. So these are the interpolation errors for standard polynomials. And that's the basis for finite element error estimates. That's how it works. That's why I wanted to introduce this big U idea, because in finite elements, we solve for little u, which we know is best approximation in the space. But the unique interpolating polynomial also lives in that space. So you know that you get these sequence of bounds, right? And that's how you build up the estimates on the error, the a priori error estimates. So that's this whole picture like comes together, Yeah.
Dr. Scott, will you say that the Runge's phenomenon also depends upon the basis that we are choosing? Because you said that with splines we can reduce the Runge's phenomenon, and I thought you said earlier that the interpolation polynomial is unique to the basis we choose. It just depends upon the points and the degree.
Yeah, but the points depend on the basis. Yeah, exactly. So if you go to Chebyshev, they have this phenomenon right here, that the zeros optimize polynomial interpolation in the sense that the resulting interpolating polynomial minimizes Runge's phenomenon, provides as close to the best approximation to a continuous function under the maximum norm. Okay. So when you pick those points, right, it's in the background, it's like you have that unique interpolating polynomial. When you pick those points, it's like writing that interpolating polynomial in the Chebyshev basis with respect to those zeros. It doesn't really matter what basis you use, right? But those points do matter. Yeah, that's the interesting thing, is that those points are like significant. Oh, good. That's really good.
Thanks for taking some extra time, Dr. Scott.
Yep, no problem. Yeah, who's still on? All right, well, let's stop there for the day. Thanks, everybody.
All right, thank you.
Well, thank you.